Cool. All right. All right. Okay, so I'm streaming and I don't know if you guys can see me right now. So we're just gonna do it. Welcome to the AI Core first online stream. And basically today we're gonna go through convolutional neural networks. So basically this is some software which we've been developing for the last week. It's probably going to be extremely buggy, and we're going to basically give out a form so you guys can let us know what if anything goes wrong with this, and then basically we'll strive to improve it. But basically let me just show you around. So what we have here is the this is my screen, so obviously you guys are just watching me do that. There's you can make questions and comments here, and basically go ahead and do that. You can switch between being in the classroom, so just observing me, and being with your group. So hopefully you'll be able to see people pop in here in your lobby like that, hello, and basically then you can move between those two lobbies. So what I am going to do is I'm just gonna basically wait a few minutes and see what happens. Just wait for a few people to come along and basically make sure the rest of my team is set up and that kind of thing. So then we'll just start in a few minutes. But yeah, please like make a comment, let me know you're here or something, and let me know if anything is obviously going wrong, please. But for now, yeah. Okay, thank you for that, Harun. I was muted. Basically, okay, yeah, so just to say that again, what we want to do is find this this section on the AI Core web app. Just go to code, the deep learning series, and then the week 3 convolutional neural networks. Click link to code. That'll take you to here. Well, it'll take you to this file. Just click the repo and then click clone or download. Yeah. So I have re-downloaded that. Well, I'm doing so now. Must have got the data set in still. That's why it's taking so long. But yeah, just make sure you've done that, and then we'll be ready to go. And yeah, keep me updated with how it's going on the forum as well. That's what it looks like from our end currently. Cool, yeah, so it's the teacher's lounge, and it's Killian who's helping me out today. It's Vesh as well who's here, and Harun. The idea is that you should be able to basically be in a lobby with different people, and we as teaching instructors can move around these lobbies and ask questions and that kind of thing, as we're used to in class and as we think is really helpful. So ideally, you guys should all be able to hear each other and talk to each other now, but I'm not sure about that. Echo lag, very serious. Okay, there's Vesh. Alright, I'll try and close this stuff. Okay. Harun, keep me updated if anything serious is happening. Right, cool. So what I've done now is I've cloned this repo, and now we want to start that. So you want to open Jupyter Notebook. Either do that through Conda, open Anaconda and click launch on Jupyter Notebook, or just run it like this in your terminal if your machine can do that. And then basically find the repo which you just downloaded, go inside there, and then go into what we're going to be doing today is convolutional neural networks. So this is the notebook without the solutions. There's also one with the solutions if you get stuck at any point. So yeah, I don't think the lobbies are working right now. It's the first spike test we've done, so it might be hard to ask questions at this point, but we'll definitely get that sorted before next time. Otherwise, like please feel free to I don't know, set up any group calls between anyone else you know who's also attending and talk about it, because we think that's really good way to get your understanding of it. But yeah, basically what we're going to do is we're going to go through this notebook. So, oh man, I would really love to be asking questions back and forth here, but I can't do that. Okay, so what's wrong with how neural networks process images? Is a question. We saw previously that neural networks take in vectors of inputs. So we have a bunch of different features, and they're all in a vector, so it's essentially a list of different features, and the neural network takes in each of those different features at a different input node. But they have to be a vector. So when we did this before, what we did was we were classifying the handwritten digits in the MNIST dataset, and those obviously are not vectors, they're images, they're 2D, so not only do they vary in one direction like a vector, but also another direction, they're like matrices, and even more than that, they have different color channels, so they're basically stacks of matrices. Point is, they're not vectors. So what we had to do to process images with neural networks was to flatten them, and that was stack all the rows together, so that they become just one long list of features, a vector. And then we could pass those flattened images into the neural network. And yeah, basically that has a few problems, and so, which I'm going to describe here. So basically, one point is about spatially structured data. So for example, in an image, a lot of the information comes not from the actual values of the pixels, but it comes from the spatial relationship between the pixels. Yeah, whatever in here is, for some problems, like the order of the features doesn't matter. So if we're talking some, person data set where we have their age, height, and the hair length, it doesn't matter what order I pass those in. They still represent the same thing, and the neural network can still learn to find the correct weights for those different features. It doesn't matter what position the features are in. But it's not the case for images. If we randomly reorder the pixels in an image, it's likely going to be totally unrecognizable. Most of the useful information in the image comes not from the values, like I said, but from their relative positions. And this, obviously what that means is like, well, the relative positions of different pixels make up edges, and those make up objects, and those make up actually what the content of the image is. And so not only are images subject to this problem, but also other spatially structured data such as videos, sound waves, medical scans, 3D models, etc. Every different point in a video or in a 3D model is, what it means. The meaning it has is due to the position of that value in the image, not necessarily the actual numerical value itself. And so, what happened when we flattened the vector? I think I probably have a drawing of this. Okay, no, I don't. What happened when we flattened the image before is that we basically lose all that spatial structure. So we're just stacking the rows of an image on top of each other, and that means that the rows across different, the positions of pixels across different rows are going to be totally scrambled by doing that. And this means that we lose a lot of the really valuable information about the data. So so that's basically a really major problem with processing images as using neural networks by flattening them. And another issue is that, or another thing which you can easily understand why neural networks are being extremely inefficient, is that if you, say, are looking for a particular pattern or person or face or whatever in the image, you basically want to take the features around that location in the image and find the weights which give you a meaningful representation of whether that face is there or not. And this means that you might be looking for the same thing in different places across the image. Now, if you flatten the input, an image, into a vector, then you're going to have to basically have the same weights at different positions along this vector to make sure that you're looking for that same feature across the whole input. But it's easy to understand that what would be better is to just use the same feature, the same weights, to identify that same feature and use those weights across the image. And this is called weight sharing. In our case, weight sharing across space, across the image. So you have some particular values that look for a certain pattern like that, and basically these will be the different weights, and basically you want to apply these weights to all the regions of the image, not just a single location. So but with a neural network, with a flattened vector, you have to basically learn the weights across the position independently. There's no way you can reuse them. So this will all become much clearer whilst this will become much clearer whilst we go on. Who's calling me from Glasgow? Don't need that. Okay. So what else do we have? I guess it's going to be questions and stuff I should look at now. Cool. Yeah. All right. So what our prior understanding of how image data should be processed, using our prior understanding of how image data should be processed spatially, we'd like to find some kind of model that can retain the spatial structure of our input rather than squash it so that it gets flattened. This will become much clearer when we go into the code and look at these diagrams. So basically, firstly, what is an image? what's an image as data? Images not naturally vectors. Like I said, they have not just a height, but also a width. And in the case of color images, they have different channels, which contain the intensity for the different colors. So the first channel is a matrix, which has height and width, and each value within that 2D grid represents the intensity, so maybe between 0 and 1, or between 0 and 255, of how red is this particular pixel. In the next channel, here's the blue channel, we have the same thing, where across the whole spatial range of the image, the values represent how blue is this pixel. And then the combination of those three things, RGB, make up the actual color that you see. So here is basically this image destructured into its RGB channels. So yeah, and then you might also have PNG images with transparent backgrounds. There might be another channel which represents the opacity of that pixel. So obviously this is a course on deep learning, but let's just talk about quickly, how was computer vision done before deep learning? Basically, what people would do is they would draw their own patterns. They would draw their own patterns like this that they thought might be a good kind of pattern to look for across the image to identify faces. And this means that people had to use their own intuition to figure to try and guess basically what is going to be a useful feature for me to look for. And then they would pass this this filter, it's meant to be a face, all across the image and basically see where the high values in the image match the high values in the filter. So yeah, these are what are called filters or kernels, basically looking for certain particular patterns. So if we're looking for a vertical line, where say it's bright colors, so we're looking for a bright vertical line with dark edges, then we would have a filter with low values on the outsides and high values along that vertical bar. So that yeah, basically when we pass this over an image and these high values are matched with high values in the image, then it's meant to be like, okay, cool, this feature is present in this location. So yeah, basically, how do we do that? Like I said, how do we match the how do we check numerically, is it a good match? Well, we want to see where the high values are aligned with high values. And so basically a simple way to do that is to take the dot product. So if you were to do that is the element-wise multiplication and sum between this filter and the pixels which are overlays on an image, then you should get high values where this feature is present. Yeah, cool. So yeah, basically every filter, you can have filters of different sizes. This is a 5x5 filter or a 5x5 kernel. And basically, yeah, you're going to just move that all the way across the image, which looks like this, basically. So here we have some kernel, which has ones where there is white and negative ones where it's dark. Basically, what this means is that this filter is looking for this X pattern, is looking for a bright X pattern in the image. What we do with it is we take it, apply it to the image at the first location we can, top left, and then move the filter across the image until we get to the end, then move it down one and move it across here. So we basically apply it to every possible location that we can do within an image and see where it's matched. And then you get these element-wise sum. So we're doing 1 times 0, minus 1 times 0, 1 times 1, minus 1 times 0, and basically sum those up for the whole filter in that particular location. And what that gives you is basically a single number for each location which you applied that filter, and then if you do that over many different locations, it gets you a grid of outputs, which are basically meant to be summaries of how well is the filter matched in this location. So it'd be really useful if I could pause it, but in the top left, say, okay, it's not matched very much. In the middle top, yeah, it's matched much more. In this location here, wait, no, not that location. where's the, yeah, sorry, here's that location. So here is an X in the image, a bright X of 1s. And this is the same pattern which is in our kernel. So when we take this kernel and apply it to this location, we'll see we get a very high value, this 5 here. That's because it's matched as high as well as it can be. So the dot product between the filter and this region of the image is as high as possible. And this -3 in the middle comes from it not being matched very much at all. It's only matched in one location there. Cool. So I hope everybody's asking questions and getting them answered. Yeah, cool. All right. Just let me know if that's working. Cool. Yeah. I'm sure Haroon, Vesh, and Killian will be at your side if you need that. But yeah, I'm kind of like out of the loop here. This is really annoying. I wanted to be able to like move between the lobbies, but I don't think they're working. So yeah, guys helping me out. Just give me a message on WhatsApp or something. Let me know what's going on. If I can re-explain anything like that. Okay, cool. So yeah. So basically this is how computer vision was done before. People would draw these filters for themselves and then basically try and move them over images and see where they're matched. And maybe if they're matched in one particular location, we'll say, cool, this feature is present here. And maybe that'll be helpful for me to do my task. Maybe it's maybe it's some classification where I'm looking for some particular filter. I can move that filter across and see if it's matched above some threshold. So this even back before deep learning, it was people would use the convolution operation, which is where you take these filters, move them across the images, and see where they're matched. Okay, cool. So there's a few different parameters of this convolution operation. One of them is called the stride, and this is basically the number of pixels which you shift the kernel every time that we move it. So in our case, we're only moving the kernel one step to the right every time, so the next position is going to be here. That is, we have a stride of 1. If we moved it from the top left all the way to the top right, then we'd have a stride of 2. I think that's shown in this diagram here. Yeah, so stride is basically the step size of the filter. So why might you want to do that? Well, one reason is that if you take bigger step sizes, you're going to have less regions to process, which means that the computation of this convolution will be faster because you have to do less calculation. Okay, what other features do we have? We have padding. So this is where we add. One way to do it is to add zeros around the edge of an image. And the first idea about why you might do this is that if we think about without padding, this 3x3 kernel is firstly going to be placed in this region. And in the next one, it's going to be placed in this one. And then once it goes to the next row, it's going to be placed down here. And this pixel in the top left will only ever have only been ever included in one of those convolutions. So it's kind of like, it's unfair. This middle pixel is going to be processed in this filter location, in the next one, in the one after, and when you get onto the next row, and even when you get onto the next row after. So this final value is going to have much more contribution in the feature map, which is output, and that's what this is. This is called a feature map. Yeah. So or an activation map. So basically, basically the grid of matches is that activation map or feature map. Cool. Yeah. So we have stride, which is step size of the kernel. Padding, which is do we add any anything around the edges to make the image larger. One reason to think we might do that is so that all pixels get treated fairly. Another reason to do this is that the output of a convolution over some image like this will always be smaller than the input image. Now, we know that neural networks, what they do is they build up hierarchically complex features. So what we're going to do is we're going to replace our linear layers with convolutional layers, so that instead of passing in a vector and getting out a vector, we're going to pass in some image like this and get out this. That will be our convolutional layer. And basically, what we're going to learn is these filters. These filters basically contain weights, which say how, what pattern am I looking for in any particular region. And just like we did with the weights of a neural network, we're going to learn these weights for a convolutional neural network. It's really simple. It's really not very much different to what we've done previously. And yeah, okay, so what I'm talking about here is that every time we do a convolution, the output is smaller than the input. This means that if we want to build up successive layers of more and more complex features, well, we might want to do that several times to build up complex features. So we want to have like a deeper model, so we can have like more layers of abstraction. But if the image gets reduced in size every time it gets processed, that means that we can only do this a limited number of times. For example, the output here is 3 by 3. If we're doing convolution with a 3 by 3 kernel, well then the output of a convolution over this output will be a 1 by 1. And then you can't put a 3 by 3 filter over a 1 by 1 image, because it doesn't fit, obviously. So if you add padding to the edge here, then you will actually increase the size of the output. So if we added one row of zeros all the way around this this edge, then the output would be 5 by 5. It would be the same size as the input. Okay, so and you get this equation here, which basically tells you what will the output shape be. So this is the width or height of the image, assuming they're the same, minus the stride divided by minus the width of the kernel divided by the stride plus 1. That's going to be the output. So in this case, we have a width of and height of 7, so n equals 7, k equals 3, and then stride size is 2, so we can have 7 minus 3, 4, divided by 2 is 2, plus 1, 3. So the output here is going to be 3 by 3. You could apply this in both the height and width dimension if you had different values for this n, if it were a non-square image. But yeah, that's how you can compute this, the size of the output. Not that you really need to do that. Okay. Okay. Apologies for sound issues. We'll have to figure that out later. Guys, let me know if it's any better without my headphones. But otherwise, yep, gonna keep going with this. Cool. So, yeah. Also, let me know if people are asking questions and that kind of thing. Is it better now? Yeah. Cool. All right. Good. Sweet. So, yeah. Now we can talk about. Now we know what convolution is. Basically, it's basically having these patterns that we want to find, moving them over an image, and seeing how well they're matched at that particular location by taking a dot product. Now we know what that is. Now we can basically try and define, okay, what's a convolutional layer? And this is what we're going to replace our linear layers in our neural network with. So to try and understand this diagram, firstly, I guess, what we did before was we would take our image, which was 3D in this case, it's a tensor, it's meant to be an image, and we would flatten it into a vector of an n vector, and then basically we would try and treat this vector as the input to our neural network. And this would mean that each of these inputs would have an associated weight. So for the n inputs, we would need n weights, and we would make say, I think, what have I got there? That k k different combinations of that. So just to refresh and make this much more concrete, I'm just gonna open up that. Just to remind everybody what we're talking about, if it's not obvious. Cool. So yeah, basically we were taking in these inputs. So we were taking two features, and then for each of those two features, we would have two weights leading from them to another node. And this node is basically the what we hope to be a more useful feature, which is a combination of these two inputs. Now, we don't just want to find a single feature from them. We want to find out maybe multiple things, which represent some more meaningful value. So, you take in some features of a house and you calculate some more meaningful thing, like, okay, how, maybe this feature predicts, or well, in the case of images, for example, you take in the different pixels, you hope that this layer basically gives you a representation of what edges are there. Maybe this is a vertical edge, horizontal edge, and then the next layer then basically makes combinations of those edges to form shapes, and those to form objects, and those to make a prediction for a single value, like what object is this. But basically we had each feature having a weight each. So like in this case we had n features, so we had n weights leading from them. So that n is the number of weights leading away. But then we wanted to form multiple different features from them, in this case 4. So we had 4 lots of those different weights, i.e. we had k of those. So we would make k linear combinations, that is weighted combinations of the inputs, and then store these values as new, hopefully more useful features, hopefully which we can make a prediction from. But as I explained, in this process of flattening it, we've lost most of the useful information if our data is spatially structured. And it's a known fact that images are what they are because of how the pixels relate to each other spatially. So it's like, we know this information, now we want to try and inject it into the model. And so for that, we use convolution. So instead of doing this, where we flatten it and have weights for each feature, what we're going to do is we can now keep the image as a tensor. Then basically, instead of having weights which are applied across the whole input, we have smaller weights. These are these are our filters, these are our kernels. And what we're going to do is we're going to apply them at different locations in the image. So I've tried to draw like the first one, second one, third application of this filter here. And so the first time I place this filter in the image in the top left-hand corner, I do an element-wise multiplication. So I do that element-wise multiplication to get a single number. That's the single number which goes in position 1 here. So for this feature, for this kernel, I'm going to pass it all the way across the image, and I'm going to get single values which basically tell me how much was it matched in that location. So I'll keep doing that until I fill up this whole pink grid here. And then I'm not just going to do that for one. Like I said, I don't just want to find one feature. I don't just want to have one node in my next output. I want to have many. I want to basically look for a bunch of different things in this image, not just this one. Maybe this one looks for cars, and I also want to look for animals. And so I'm going to use the car filter to identify where these features, where that feature map is found. And then I'm basically going to do the same for this other feature, which looks something else. And all of these are going to be applied at every location they can across the image, given the stride and the padding, to form a 2D grid each. It's always 2D. This is not a 3D. Each of these tiles here is 2D. It's not 3D. But basically, for each different filter, we're going to produce a 2D map, a 2D activation map. Basically tells us where did this input activate our neural network, i.e. where was this pattern found. And so this basically stack of these activation maps is going to be the output of the first convolution. Yeah. Okay. So yeah, that's that really. That's how convolution works. I'm sure you guys have questions. Like, please put them in the forum. Please just like get involved, talk to people, try and communicate with us. It's really hard, like, not being in class. We've got to stay safe. So yeah, basically that's convolution. It preserves the spatial relationship between the inputs and means that we can process images directly instead of having to flatten them. So the question is, what are these things? What am I looking for in the image? Like I said before, people had to like fine tune them manually and like draw the patterns they would look for. It's just a hopeless task, really, especially when you're considering higher dimensional data than images, like videos or like 3D models, that kind of stuff, where spatial information is really relevant. It's really critical to understanding the image. It's a hopeless task trying to design them yourself. And for ages, like, computer vision basically, it was going nowhere. It hasn't been able to solve any meaningful problems until the last 8 years, really. And but now, some people are saying like computer vision's a solved problem. Not quite true, but a lot of stuff can be done with it. We can do real-time object detection, image recognition, segmentation, that kind of thing. We'll talk a bit about those examples later. But we don't want to design them by hand. We want to learn them using backpropagation and gradient descent. So what we're going to have is that we're going to have some model similar to a neural network, but where each layer is not a vector, it's an activation map. So it's a tensor, it's a stack of activation maps, and basically this is going to then be convolved over again and again and again to produce some prediction, which then will be hopefully it will look like what we have in our data set. So it will be, if we're doing, say, a classification problem, we'll predict a single number between 0 and 1, which will classify is it or is it not a member of the class. And basically we'll compare that prediction to the label using something like binary cross entropy loss, or if it's a continuous prediction task, we'll use mean squared error to compare them. And then we can differentiate that loss and try and use gradient descent to basically understand how is this loss affected as we change the weights of our model. So what we want to find is using gradient descent, we need to basically move in the opposite direction of the gradient. So we need to find out what is the gradient of the loss with respect to each of these different values in each of these different filters. But then we know, okay, which direction should I move that weight in? And we can just do that iteratively. So we'll do the full forward pass of one example, pass it all the way through our model, compute prediction, calculate loss, calculate derivative of that loss with respect to this output, and then that output with respect to this value, and that output with respect to this weight. We'll do that for all the different weights, and then just update them with a gradient descent. Cool. I hope that makes sense so far. Just ask questions. But I'm going to keep going otherwise. So one thing that we can also do is pooling. So I'll just describe what pooling layers are before we use them. I guess I'll just read this, probably written well. Immediately after convolutional layer, it's common to apply some form of pooling, which is a technique that summarizes or downsamples the values in a local region of input, reducing the number of values in its output, and reducing the number of parameters that need to be learned for a succeeding parameterized operation, such as a further convolutional linear layer. Basically, what that means is that instead of having an example, something like this, so instead of, maybe this is the output, maybe this white region is the output from one of our convolutional layers, it has that size. Now there's still quite a lot of values here, and maybe we're finding like the model is too slow, or it's taking too much memory, that kind of thing. And so what we can do is we can say, okay, don't actually store or don't process all of these values, but maybe I want to just like summarize what's in the top left corner. So I could do something like max pooling or average pooling with a 3x3 kernel. So I could place a 3x3 grid over there and replace these 3x3 values with just a single value, either maybe the average of all of their values or the max of their values. Those are different types of pooling. And so as a result of that, well, then I will get a smaller activation map, which needs to be processed by the next layer. And hence I'll have reduced the computational resources and the memory requirements for this model being used. So that's one of the reasons why you would use pooling. It's really easy to use in PyTorch, and yeah, all it does is basically replaces lots of values with a single value. And so one reason that's useful is what I've described, making your model more efficient. But another reason it's useful is because it basically induces what's called translational invariance. So if I see a particular feature that is in this very top left corner, and then maybe I see also in another example that feature is in this top left corner, well, really what I know is that the image was that feature was in the top left. And maybe what I can do is I can just say, I can pool this region and summarize, like, basically, was this feature present at all? And by doing that, what it means is that you can basically say, yes, I think the image was present in this top left, regardless whether it was here or here, because they're like minor differences. And the layer succeeding this one might only need to know that, yeah, okay, it's in the top left somewhere. I don't need to be very specific, especially if I'm doing something like a classification task where I just need to know, was the feature present at all? I don't need to know the exact position of it. So that might be an example of where you pool some of your layer outputs. Cool. So what else we can talk about? So yeah, there's max pooling and average pooling. Just basically, they just either take the max of the region that you pool or the average. You can see the docs here, and yeah, what is this about? So yeah, basically convolutional networks, like as you have seen kind of here, they maintain spatial structure throughout the model, which means that you can do things like image segmentation. So you don't have to predict a single value or a vector of values, but you can actually produce an output predicted image. So if you want to do image segmentation, that is where you mark everywhere on an image what class is that particular image. So maybe you want to draw like an outline of the person or something like that. That'll be an image segmentation task. And so what you can do with that is basically you can output an image where, say it's just like, say the only thing you're looking for is people, well then you would just have an image the same size as the input, a 2D grid, and then all of those values in that prediction would be like confidence values between 0 and 1, telling you do I think this pixel is a member of the person class, if you're doing like person detection, that kind of thing. So yeah, now using these, you can solve problems where the output is an image. Like you can predict an image, or you maybe you want to like do some kind of image translation. Like you want a classic example, like take in images of horses and output images, the same image of horses, but instead of horses, they're zebras, that kind of thing. So you can make predictions where the output is an image. Cool. So what we're going to do basically is we're going to perform image classification for 10 classes by using the MNIST dataset. That is a dataset of handwritten digits. Basically we're going to output a vector of numbers which represents the confidence of that particular input being a member of this class. So yeah, we've done this stuff before. Yeah, I would usually ask someone to explain it, but basically I'll do it. So what it does is just import the stuff we need. So Torch, that is our deep learning library. Torch Vision, this basically Torch's computer vision library, has things like data sets, has ways of transforming the images. We'll do some plotting, so we get pyplot, NumPy, some math, and then summary writer. We're going to use TensorBoard to basically display our loss curve as we go. So the first thing we do is we get the training data. Now, Torch Vision comes with some data sets. One of them is the MNIST. That's the handwritten digits I spoke about. And basically it takes these arguments, takes the root, like where do you want me to store the data? Because it's going to download it if you don't already have it. What transforms should I apply to these images? So the images come as PIL images, Python Image Library images. And what we want to do is we want to process them with a Torch model. We're going to build a convolutional neural network in PyTorch, and that needs to process tensors. So we need to transform them using the transforms from PIL to a tensor. So basically this transform will be applied to all of the images when we get them, and in this train data list. And basically we can specify, okay, which images do we want? They are split specifically, or that there is like a known split, so that people can benchmark different algorithms using the same training and testing sets. So do we want the training set? Yes, in this case, true. This is our training data. And do we want to download them if we don't already have them? Yes. Do the same for our test data set. In this case, the only difference is that we'll, I think just download is true by default. Someone check that out for me. But yeah, in this case, train, nope, this is test. So I'll get the test. Yeah, so please run that, and then we'll get to here, and we'll print some stuff. Print a random example, and then we'll show a random, show the first image. Yeah, so if I run that cell, what's going to happen is it's going to download the MNIST dataset into this location. It's going to do some stuff, and then it's going to print, as I said, it's going to print the first example. Now, what is this? Like, just looks like a lot of zeros, but no, there's some non-zero values in there. And this, although it might not be obvious, is this. So what this is the, you can see it's a list of lists. So it's a, yeah, basically the whole thing is in a list, and then each row is well, it's basically rows and columns. That's what it is, pretty much. And you can see each of them, you can see the pixels here, and basically these different values are the pixel intensities at that point. So you see most of them are 0, that is there's no color, that is they're dark, they're black, and some of them are non-zero, some of them are actually close to 1. So 1 being the highest value, where it's like all the color, that is, it's white. That's one example in this data set looks like. So, yeah, cool. We did that, right? All we did was we got the train data, and then we got a random integer, and we indexed that data with it. And then we got the 0th item from that. And what that was the actual features, not the label. So if I, let's just do something different here. Yeah, let's say example equals that. And then we'll say x equals example to the first thing in the example. We'll print x, and then we'll also print y, which I'm going to say y is equal to the second thing in the example. So I run that. Now, did the same before, printed out the features, but it also printed me y in this case, which is a label. So x is the features and y is the label, and obviously this is the label for this image. So yeah, that's basically just getting this data set and printing an example from it. I specify the color map, so it shows up as grayscale, and yeah, basically, yeah, that's that. Then what we're going to do is we're going to split the data into training data and validation data. So we already have this the training set, and we want to be able to try out different hyperparameters on our model. So what's the best learning rate? What's the best batch size? Those kind of things. And these sort of values you don't want to optimize directly. For example, the way to get the best lowest error is to just use full batch training, but that takes way too long. You have to process the whole data set for every iteration of the weights that you want to try. So we want to basically create a validation set where we can train our model and test its performance on this validation set. And we use that to test the hyperparameters so that we don't test hyperparameters on the test set and hence bias them to our results. So yeah, Torch has a handy util in torch.utils.data called random split. Basically takes in the training data and then randomly splits or takes in whatever data set you have or whatever iterable you have, in fact, and basically splits it into two different iterables of these sizes. So these two, the length of all the integers in this list must sum to the total length of this value. And then basically what we're going to do, now we've got our training data, validation data, and test data, we're going to make these data loaders. So these will basically just batch up the data for us into a given batch size, and then also shuffle it so that every time what we want to do is we want to do like many epochs over the whole data set. That is, we want to basically process the whole data set and train the model as we do that bit by bit, and the size of those bits is the batch size. So we're just going to iterate over this data loader. So previously we even did this manually to show what it is, but it's just batching things together so that the model will process 128 image examples at a time, average the loss for all of those, and then try and it will find the gradient of that average loss with respect to all the weights of the model. Then it will move those weights in the opposite direction. Just use gradient descent as usual. So cool. Simple. I think we've done that before. There's a video on the AI core about that if you don't already get that. But yeah, just make sure you understand that. And now is time to build a convolutional neural network. So the comments are here, and this is basically what we want to do. So yeah, please have a go at that. This is a code break, and then I'll come back in 15 minutes, I guess, or I'll just be floating around here, but we'll resume and I'll fill in the answers in 15 minutes and then we'll go on to the next section. But yeah, basically same thing as before. So we want to make a class like we did the neural network, and it's going to basically be initialized with some stuff. In this case, we're going to make some convolutional layers as well as fully connected layers. And then we're going to define the forward function. So this is what happens to the data X when it's given to the model. So yeah, have a go at that. And any questions, put them in the chats. All right, yeah. Some really good questions. So I'm just gonna go through a few of them whilst I hope you guys are coding away. Yeah. So are all kernels applied to 3 dimensions separately? No. The kernels are almost always, their depth is the same as the depth of the layer which they're processing. So and note, there's a few things there. Like one, if I go to this diagram, the first thing is that what I'm saying is that the depth, that is in this case where our image has 3 channels, that is the depth of the kernel. It's always the same. So the kernel will basically look for features through all of the different channels. Basically, yeah, so it will make a combination of, the blue intensities, the red intensities, and the green intensities to actually make a form a useful matching value from that. The other interesting thing is that this is just an example for the first layer where our input is the image. Now, the output of this convolutional layer looks like this, right? And this one has 4 channels. And this is going to be the input to a next convolutional layer. So all of the weights, the kernels and filters in the next convolutional layer are going to have 4 channels, not 3. And those kernels are going to be applied to basically go all the way through the full depth of the activation map. And in that way, they can combine many different features, just like our neural networks were combining these 2 features. So all of these, more complex features here are a combination of these input features. And we want the same thing for our convolutional layers, right? We want to be able to, basically each of these different tiles, they represent certain features. And we want to be able to combine features, and it might be the combination of those features which means something useful for our actual prediction problem. Yeah, so that was a great question. What else? Are CNNs just for images? No, not at all. They work great for images, and it's an easy visual example to understand. But you could also do the same thing for video. You could do the same thing for text. So, and the idea is that it's basically they're useful anywhere where you have the prior knowledge that your model is that your data is spatially structured. That's where they're useful. So in example like text, every letter is like, it doesn't matter the actual value of the letter, it matters the relative position of all of them. Images is obviously the same thing. Pixels, like it's not their values that matter, it's their location. What else? Video, like it's not just the pixels at a certain, it's not just the value of the pixels at a certain point in time, it's how they relate to each other through time and through space. Like the convolutional neural networks can be used for so many different things. Say you want to process like a 3D CAT scan of someone, then you could use 3D convolution for that. Image would be an example of 1D convolution. Text would be 1D convolution. In the case of images, we're doing, I keep saying that now, like 2D convolution. What does that mean? It means that we move the filter in 2 directions. So we move it across the width and through the height. In the case of text, well, we just have, one line of sentence to read, so that would just be one convolution. And the point here is that we're using the same weights across different across that dimension, across different positions along that dimension. And then in the case of like processing 3D models or something like that, then you'd convolve in the X, Y, and Z direction to basically get representations of where are these features matched in 3D space. So yeah, another good question. I don't know, let me know how the sound is now as well. The training and testing data set is the same. Sorry, is the training testing data set the same? Well, they're from the same data set, but they're different data points. Yeah, exactly. Thanks, whoever replied that. So it's just like different examples. It's like say we had just like a data set of size 10, and the first 5 maybe it contains like a 1, a 2, a 3, a 1, and a 4, and then the training set will be similar examples, again handwritten digits, but just not the same examples. It'll be different examples, but from the same data set, and hopefully the same data distribution. How is a CNN different from a normal NN? In the fact that it processes non-vector data, basically. Yeah. So yeah, where a regular neural network takes in a vector as input, convolutional neural network takes in multi-dimensional data. Yeah. Cool. So yeah, and it outputs these feature maps, which are like in the same dimension, in the same number of dimensions as the input. So if we have if we're doing 2D convolution, every weight produces a 2D activation map, and then however many of those weights we have produces a different activation map, and we stack those together. So our output in this case is not a vector as in a neural network, but it is a stack of 2D vectors. Cool. Yeah, that's exactly right. The train parameter is Boolean, true or false, and it basically just tells Torch like, do I want the training set? If not, give me the testing set. And they're just like they're just like predefined splits, so that everybody who's trying to prove they got the best algorithm is benchmarking on the same data. Cool. I like that question. Love that question. Love that question. All right, cool. Oh, this is great. Yeah. What about the bias? Do we just update the weights? Like, it's the same thing for the bias. So yeah, I've kind of implicitly assumed that you'll get that there's a bias, but that's not necessarily true. So just like in a neural network, we're weighting each feature by a weight in our filter in this case, and then we're taking a sum all of that weighted combination, and then so that's the weight part. But then also, yes, we're adding a bias as well. So this value here is not only the weighted combination of this kernel with those pixels in the image, but also plus a bias. So it's a single number for each of these weights, because the weighted combination produces a scalar, and then we add a bias to that. So each of these weights, each of these kernels has a single bias. Multiple weights, in this case, like k by k by c weights, and then plus 1. So plus 1, that 1 comes from the bias, which is then added to this. That's how many parameters we'll have. My housemate's on the roof. All right. Cool. The kernel was applied in a 2D patch of an image before being translated and applied to a different patch. Exactly. You repeat this until you have applied the kernel of the whole image. Not sure I understood this reply. my question was, if the kernel is 2D and it generates a 2D image output, do we need to apply it to all three RGB layers separately and generate 3 outputs per kernel? Yeah, so there is a different way, not commonly done, but what you can have is, so I think what you're describing here is, what if we had a 2D kernel and we applied that same 2D kernel to each different layer? I don't think you would do this very often, or at all, because the features that you'll be if that would work, your image may as well be grayscale, right? Because you'd just be looking for the same features across the different color channels, I think. But what is actually sometimes done is that you have a kernel which is the full depth of the input activation map, and you only apply you only apply, I should forget how that happens, but I think it's like each layer is only weighted by its corresponding layer in the output, and then you produce a 3D activation map per convolution. Not very commonly done though. Yeah, so basically in this case, like we're not going to have a 2D kernel, we're going to have a 3D kernel. It has both height and width, that is like the spatial region which we're looking at in the instance of images, and it has a depth, which is the full depth of the input activation map, which might not necessarily be 3, right? It might have more activation maps which is going to process. I'll let you get off the call. Yeah, what about the bias? Again, same as the other question. Yeah, how can the stack of vectors classify or predict the image? Right, stack of 2D vectors can be said to represent the features of the image as a whole. So a neural network can be taught to simply map certain combinations of features to a certain label using supervised learning. Yeah, basically. Nice. Okay. Cool. All right. Yeah, keep the questions coming. And I will continue. I don't know. Like, okay, I'll just trust like some of you did this and some of you got it right. What are we trying to do here? So yeah, but I think basically these lines are just describing how it is you use the conv2d class in PyTorch, but we can look at the docs as well, which is always a good thing to do. So here's max pooling, explains what's happening there. What we want to find is conv2d. Cool, right, so here is the docs for the conv2d class in PyTorch. So if I hadn't seen this before, maybe like some of you, first thing I would have done is come to here and basically find out, okay, how do I use 2D convolution in Torch? And so, yeah, basically it works like this. I'm gonna get torch.nn.conv2d. I'm gonna basically say this layer I'm gonna tell it how many layers do I expect, how many channels do I expect the first layer to have. In our case, we got a grayscale image, so there's only one channel. If this were an RGB image, then we'd have RGB channel, 3 channels here, so that would be 3. Out channels, so this, just like in our neural network where the output of each layer was the number of features we wanted to find, this out channels is basically the number of weights, the number of kernels which we want to apply, i.e. the number of different things we want to look for in our input. Kernel size, so by default assumes that they're square. So if you give this you can give this an integer and it'll assume that the kernel has that value for the height and the width. Or you can give it a tuple, so just a pair of numbers, so brackets, height, comma, width. If you want to use non-square kernels. Stride, so yeah, what's the step size? By default 1. Padding, do we want to add any padding? By default no. Not sure what the others do. I mean, there's a flag there for whether you want to bias or not. There's also padding mode. So it's probably a nice example of this. But you don't just have to pad with zeros. You can pad with different things. Okay, I won't bother if I can't find an example quickly. But you don't just have to surround it with zeros. You can surround it with, you don't have to just add zeros around the edge. You can, for example, take the value of the pixel and extend it all the way out. So this one's a 5, you'd have a 5 here and a 5 here, and this one's a 6, you'd have a 6 here. And then you can also choose basically, what this padding number here specifies is how much padding, like how many layers of zeros. So if we had multiple layers of zeros, or multiple layers of padding around the edge, then we could also specify another padding type called like reflect, I think is what it's called. And this basically would take the values on the inside and reflect them on the outside. I don't really have any good answers for why you would do any of them, but again, it's just a hyperparameter and you should experiment with that. Just train multiple models and evaluate them. And so, okay, cool, right, yeah. So the point of looking at docs was so that I can get an idea of how to use this conv2d. Now I know how to do that. Let's make the first conv2d layer. So it's going to be torch.nn.conv2d. And okay, how many channels do I expect in? Well, I just want one in because I've got a grayscale image, so there's only one image which specifies the intensity of the pixels. How many channels out? Well, we can choose here, right? So it's like how many weights, how many filters am I going to apply to this image? Let's just say 64 to start with. Kernel size, we can say 3. I'm just choosing them randomly. And okay, so I don't know, guys, have a think. Do you remember like how the sequential torch.sequential works? Think about that for a sec. Love it if someone could reply, but it's probably too quick. Is there a difference? torch.conv2d and torch.conv2d. I don't know if there is a. If there is, I think they're the same thing. I mean, this is the class conv2d, right? So what's going to happen is you're basically going to specify these parameters, which then tell it how many weights and biases should I generate. And what it will do is, this is a class, right? So when you give it those values, you're instantiating the class, and in its constructor, it will basically randomly generate those randomly generate the initial weights, and what it returns you is an instance of a class which is callable. That is, what's returned from this can be put brackets on the end and given some input, and then the conv2d layer will process that input by doing 2D convolution over it. Okay, so now you've had to think about it. I'm sure shouted out answers. Torch.nn.sequential, what it does is it takes in, it basically asks for a list of callable objects, which are going to be then called on the input, so basically, yeah, it takes in a list of callable objects, which will be applied sequentially when what is returned from sequential is called. So we'll see that in a sec, but let's just do this first. So we'll do torch.nn.relu. I think it's like that. Second conv layer, torch.nn.conv2d. And then, okay, how many channels is this one going to take in? So the output of our previous one is what we specified here. That was the number of filters which we convolved over the input, and so basically that's how many activation maps we're going to take. And as you can see in this diagram, that's going to be the depth, the number of channels that our next input should expect. So we will put 64 here, and then let's say we go to 128. So we've got 128 different kernels in the next layer, and they have size 3. And need commas between all these arguments. And then we're going to apply another activation function, torch.nn.relu. So yeah, again, this is the relu class. So here I'm instantiating this class, and then it returned me a callable object. Okay. So down here, basically, I'm going to take the input and I am going to pass it through the convolutional layers. So I've got this thing now called self.convlayers. Layers, and basically that's going to take in my input to this function x. So forward is what's called when we call our model. So again, I will show this example, but like what we're going to do is we're going to like make an instance of the CNN by doing conv.net like that, and basically this is going to be callable. So we're going to be able to give it some image there, and what this does is defined by this forward. So this image will be taken in as this x, be passed through our convolutional layers, and so on, right? So yeah, in addition to the answer we gave about someone's question regarding how do we use the activation maps to make a prediction, well, depending on what the prediction is, right, depending on what the problem is, that determines the size of the output. And basically, we need to get the output of these conv layers to that size. In our case, the size which we want is a 10 vector. So we want a vector of 10 numbers, which are the probabilities of that input being a member of that class, 0 to 9. And so that is not 2D output, right? It's not going to be output from a conv layer, because they output tensors, not vectors. So what we're going to do is we're going to flatten it, and then we're going to pass it through our linear layer. So note here, like I said, like we don't want to flatten it before. That's what we were doing to pass things through our neural network. But now I'm saying flatten it. So why is that? Well, it's because I'm assuming we already got most of the juice out of the information provided by the spatial relationships between the input features, right? So I'm assuming that we've already extracted that. We've already extracted that into much less numbers. So like I said, every time we do convolution, we're reducing the size of the input. We're summarizing the very large amount of extremely low-level features, that is the raw pixels. We're summarizing them into more useful features, like what edges are there, what objects are there, and then now we have those represented as numbers. So we might at this point just have like 16 numbers which represent something really meaningful, like the model's confidence that there is a person in this image or something like that. And these are, like we saw before, like I mentioned before, it's like those are then examples of features which are not, where most of the information is not spatially dependent on them, right? We've extracted all of that out already and just got the raw numbers that we can use to make predictions from directly. They might still need combining and to make some more useful features from them, so we're going to have another linear layer here. But yeah, this is why we can flatten things here. So we're going to need to define these fully connected layers. So anyone remember how to do that? Chuck it in quick. What is the function? What is the class I need to call? Oh no, what's happened? Okay, you get away with it this time. But torch.nn.linear is what you want to do. So here is the linear layers we were using before, and here is the conv layers we're using now. So it's like, again, really simple interface just to make them. And so what linear asks for is how many inputs go into this layer. Like if we're talking about this layer here, how many inputs and how many outputs. So how many inputs? Well, how many inputs are there going to be, right? It's going to be the output of this final convolution flattened. That's going to be how many inputs there are. The thing is, I could calculate it using that formula, which I showed before, which is the n minus, so width or height of the image minus the size of the kernel divided by the stride plus 1. I could calculate that through each layer and find the number of dimensions of this output, but what I can do is I can just put a random number, and then I can wait for Torch to throw me an error, and then it will tell me, hey, you put 4,893, it should have been this, and then I'll just put that in there. Okay, so what needs to happen now? Just check what's going on. All right, cool. Yeah, okay, cool. So I'm basically going to get that number from Torch throwing an error and telling me what it is. Then how many outputs do I want from this? Well, let's say I want like 32, and then I'll do another Torch dot nn dot linear. So I'm going to have 2 linear layers here, and this one is going to take in those 32 features, and it's going to output a 10 vector, right? Because we've got 10 different classes. And then finally, what we're going to do is we're going to apply softmax, but we're going to do that down here. So here we can do x dot view. Now the size of this, remember all the inputs to our model, they're going to be in batches. So the first dimension is how many batches there are. Now I could put like batch size here, but that's going to give us an error, or it might give us an error if the size of the data set is not an integer multiple of the batch sizes, because that means I'll get to the end and say I'm using batch size 100, there'll only be like 30 left, and then it will say, okay, this can't be 100 because there's only 30 here. So I'm going to say -1, which means like do whatever you need. And then I'm going to say yeah, I think so. Basically what we're going to do is this needs to be the same as the size of this of the flatten of the output of this, right? Which is flattened. So we'll get to that when it comes. I'm just gonna put a random number there for now. Linear layers, cool. We're gonna do the same as well. Fully connected layers. Gonna pass x through them now that it's been flattened, and then we're going to do a softmax activation function on the outputs. What does a softmax do? Okay, bugs. All right, so okay, right, yeah. So I need to do softmax. So I need to do did I import? Yeah, torchline.functional as f. So I'm going to do f dot softmax on x. And what does a softmax do? Well, it takes every element in a vector, it exponentiates it. That is, it puts e to the power of it. This makes it positive, and then it divides by the sum of all the elements in that vector. And this basically means that the output is going to be only numbers between 0 and 1, and it's going to sum to 1. That is, it represents a probability distribution. Okay, cool. So like I said, we've just put random numbers in here and here now. It's going to throw some errors, and we're going to basically be able to debug them, because it's going to tell us what numbers they should be instead. Cool. So I've defined the model. Okay, if you're still with me, great. I couldn't find the ID of undefined. Yep. Yeah. Where? You can't see it, can you, anymore? It's down. Is it down? Okay, cool. Okay. Yeah, get on the phone to Christian. He can send it. Alright, nice one. It's gonna take some fixing later. Okay. Yeah, if you're still here, great. Basically what happened there is a problem with the forum, so I just removed it. I'm just re-uploading that now. Yeah, please join on Twitch if it still doesn't work for you. Otherwise, yeah, you can just come back to it now. It should work. Right. So yeah, we'll just give a few minutes. Let people get back to it. But yeah, please put any questions in the forum now, and I'll try and reply to them. What's your WhatsApp? Thank you. I like that one. It's not working. Okay. Yeah, Twitch was on the whole time. Live debug. The site is still up now, so you can go and see that. Okay, cool. 17 people back. Just give it a little wait. But yeah, throw any questions you have now, and I'll try and answer them. Works now. Yep. All right, let's do it. Where did I get to? I don't know. Basically, what we've done is we had defined our convolutional layers here. So we'd instantiated this class telling Torch the size of our, how many channels we expect in, how many channels we expect out, and the size of the kernel. All of this defines how many weights need to be in that layer. So when we initialize this class, Torch creates those parameters. And we did the same for our sequential layers. And then we defined our forward function, which is what happens to anything that our model is called upon. It takes in that input, which in our case is going to be an image, passes it through the conv layers, reshapes it, flattens it out, and then passes it through the fully connected layers, and then applies a softmax to it. So, and we didn't know this number, so I just put a random one there for now, and we didn't know this number, so again, I just put a random one. And we're going to get an error which can tell us it's wrong, and it'll tell us which one is right. So here, basically, just like setting up GPU, if you want, if you have, set the learning rate, set the number of epochs, number of runs through the whole data set, create our convolutional net, put it on the GPU if we have them, then initialize our criterion. So we're going to use cross entropy loss in this case. It's a classification problem. And then we're going to define our optimizer. So we're going to use Adam optimizer. And the first argument here is what should it optimize? What should it look for the .grad attribute and use to update if, according to the Adam algorithm? And what's the learning rate it should start with? We're also going to set up summary writer. So we initialize that summary writer, which basically is going to write to TensorBoard. So I can go tensor. I need to be in the right directory. If I just go TensorBoard log directory equals runs, open that. That will start TensorBoard. And yeah, it hasn't done anything yet, so there's no data there. Cool. So yeah, that's what that cells does. Simple. It's a pretty fat model, probably why it took a while. Cool, so now we're going to train it, basically. How does this function work? Is there anything we need to fill in? No, this is all filled in. So yeah, basically for however many runs through the whole data set we want, go through the data loader. So that's basically a whole run through the data set if we iterate over this whole thing. It gives us, when we enumerate it, it gives us the index of the batch we're on currently, and then the batch, which is batched inputs and labels for a bunch of examples. Then we put those on the GPU, and then we make a prediction by passing the inputs through our model, which we pass in here as a first argument. And we should define up here as well. So we called it CNN. Let's do CNN equals conv, what do we call it? Convnet. And then we're going to pass in CNN to this training function. So pass the model, pass the inputs through the model, make a prediction, and then calculate a loss using the cross entropy loss, which compares the prediction and the labels. And then we've got this flag, verbose equals true. So basically it's going to, if true, tell us what you're doing, tell us what epoch you're on, batch, and what the loss is currently. Then we will zero the .grad attribute of all the parameters which the optimizer is watching, because otherwise they accumulate and they will store the previously now stale gradients. And then we'll do loss.backward. So this basically assigns or accumulates the .grad attribute in each of the torch tensors. And then we'll do optimizer.step. So given the algorithm, Adam, it will take an optimization step given that update rule. And then we'll use our summary writer to add a scalar to a particular chart. And this will basically plot it'll plot it on the loss train chart. And then we'll plot our loss against against basically the current batch. So this is epoch multiplied by the total number of batches plus the current batch in this epoch. So now we run this and it gives us error. So yeah, CUDA dot float tensor, torch dot float tensor should be the same. So this is because we need to put the model on. Hang on, didn't we do this here? Yeah, sorry, we actually did this. We actually defined the CNN in the previous cell, so we don't need to do that. But yeah, so we've got the CNN, and what I'd missed down there was this .toDevice, and so that gave me the error saying that the torch tensors aren't the same type, which means they can't be multiplied. Basically, this one's on the GPU and this one's not. So now if I reset that CNN and then run that, and get a different error. Cool. So now this is where you can see what I was talking about. This is the random value I put. I'm basically saying there's a size mismatch. These two things are not the same size. So this value should be this. 294,912. So let's just fill that in here. Run that. And then we should go through and get a different error. Okay, that's not the one we want to fill in there. What's happening? Cool, so where is this happening? It's happening in prediction when we try and pass it through the fully connected layers. So this is probably the error here. This is this 32, and actually that is not gonna. How are we gonna get that value? So we need to basically make sure this is the right value. What do we want to do? Let's print the shape of this. Cool, so the shape was 128 by 128 by 24 by 24. So this 128, this is our batch size, right? And then the product of this is our is the size which we want that to be. So basically we can we want to say, okay, have as many batches as I gave you. So this needs to be 128, and then this needs to be that number. And I could write 128 multiplied by 24 multiplied by 24. But that means if I change any of the model, I'm going to need to rewrite that. So what we can do instead is we can do np.prod, which basically takes a product of a list, and then so we can do x.shape. So not including the batch dimension, but get me the list of the sizes of all the other dimensions, and then take a product of them. And now that should work, I think. Cool, yeah, so we got past that bit, right? And now we have another size mismatch, which is the one I talked about before. So now this one should be 7,328, 73,728. And that should go here, right? So this is the size that each example comes out as. This is the number of features which our convolutional neural network has reduced the image to, okay? Actually definitely hasn't reduced it. It's massively increased it, but that's because we're using so many activation maps. So what we're getting is much lower resolution images, but where the pixels in those images represent higher level, more abstract, more useful features. And but we're getting like many of those activation maps, because we're doing 64, and then for each of those 64 we're doing 128. So okay, if I run that now, lovely, we've got training happening, loss going down, looks good. Now we should be able to see that in TensorBoard, and there you go. So this is training the CNN, and yeah, you can see loss going down, looks good. Cool. Right, so we did it. That's that done. Yeah, okay, that's not going to work anymore, is it? I'm just going to check questions. Yeah, please put some questions before I get to it. And yeah, let us know what you think of this as well, because it's the first time we've done it online. It's all right. Like that. Multiple voices. I don't know where that's coming from. Okay, sorry, I didn't get that in time. I don't remember what it means anymore. Okay, cool. How is the voice thing? Is there still multiple voices? Or any questions about any of this? Everybody got TensorBoard working? Everybody, that's always a problem. Anybody got any errors here? Cool, mine's finished training. Mute the video. There's no sound on though. There's no output coming from my computer. It's muted anyway. Okay. Yeah. Just one thing to say. Obviously, like, yeah. Firstly, thanks for being patient whilst we get this stuff set up. We wanted to make sure that we bring the best of offline, online, and didn't want to have to resort to using Zoom or anything like that, which is clearly built for a different use case. So yeah, we spent the week building this. Unfortunately, as expected though, some of it hasn't worked today, but promise that there'll be major improvements for next time. The idea was that you'd all be able to like be in different lobbies, kind of like with the people like you're sitting next to in class who you can talk to, learn from, ask questions, that kind of thing. And that we would be able to, as the teachers, like jump between these lobbies and kind of like just hover around, ask questions, and make sure everyone's getting it, that kind of thing. So yeah, we'll make sure that works by next time. But yeah, you can switch between group and class. No one in here anymore. Everyone's on Twitch. Cool. All right. Thank you. Love it. So yeah, what now? Anybody got any issues that everyone's like following along fine, or is everybody just not coding it because there's no one making them? I'm not sure. Okay, so yeah, we did this. We trained CNN. Now the only thing left to do is compute how good it is, find the accuracy, and that's already written, so we don't really have much more to do at all. Yeah, basically, function, calculate accuracy. It takes in the model, it takes in a data loader, which you want to calculate the accuracy when the model makes predictions for the batches in that data loader. We initialize number correct is 0 to start with, and then number of examples is the length of the data loader's data set. And so, yeah, you have to do data loader.data set here, because otherwise you'll be getting the length of the data loader, which is the length of the data set divided by the number of batches. So if you've got a data set size 100 and batch size 10, well then the length of the data loader is 10. But the actual data set length is data loader.data set, length of that. So basically, yeah, for each of the feature label pairs in the data loader, we'll make a prediction. And then we will, what is this, torch.max predictions. Okay, yeah, so torch.max, what it's going to do is it's going to return you the maximum, it's going to return you, this is going to be a tuple of two things. The first one is going to be the actual maximum value, like what was the highest confidence that I got in my vector of 10 probabilities for each class. And then the second item in that tuple is going to be the actual index in that range of 10. What's the index of the value which had the maximum? And so this is what we do in this line. We get not the maximum value, but the index of the maximum value, because that's the index of the class which we want our model to have predicted. And then basically we say, okay, increment the number of correct by the sum of where the predictions equal the labels. Okay, so here we're doing axis 1 as well, because we want to basically retain the I forget the way this works always, but we don't want to do the max over the batch dimension. We want to do the max over the actual predictions. So we want to change the rows. That's what we want to do. That's why that's a 1. So the different so we want to preserve the columns. So it's row by column. So the 1 means columns. I want to take the max over the different columns. Like throughout the different what do I want to do? Each of the rows is an example in the batch, and I want to basically preserve the number of rows. So I'm going to take a max in along the rows and preserve the number of columns. Right, that's right. Always confusing. Anyway, but yeah, basically this is just saying like I want to max over the vectors, the vector predictions, not over the batches. So basically I have this vector of predictions and labels. I want to check where they're equal, and I want to sum them up, and then I want to add that integer number to the number I've got correct so far. Then just calculate a percentage by taking the number of correct divided by the number of examples, multiplying by 100. Return that percentage and print it. And we've got some errors. Cool, yeah, so float tensor, CUDA tensor. Which one is this? Train loader. Model is on the GPU. But so we probably just need this line, right? Cool. Let's just stop that so we don't get all those prints. No, I start training it again. Oh, now it's like half trained. Let's just train it again. Watch it go anyway. See if it does any differently. Not doing as well. Or is it actually? Yeah, that's the latest one. Cool. So yeah, you see it plateaus after. Yeah, plateaus pretty quick. Question is, how good does it get here? If it gets pretty good, then that's cool. We can probably stop. Otherwise, we should probably change the model architecture and figure out something that actually works a bit better. It's not a very deep model. It's only 2 layers. It's got very small kernels so far. So yeah, it looks like that one's reaching the same plateau. I don't know how many epochs we did. Way too many. Doing pretty good. It's doing pretty good. Accuracy on the training data set, 98. Validation, just a little bit below, but yeah, pretty consistent. Accuracy, 98% on these handwritten digits. That's it. Did it. Hopefully you guys did it as well and trained a neural network. This will be available, and actually there's a video on the AI core under this workshop anyway. So yeah, that's that. I'll just hang around for a little 10 minutes or something. Ask any questions you have. Definitely want to hear them. Definitely want to hear feedback on this session as well. Let us know what you thought what did work. Obviously, we'll try to fix what didn't work, and also let us know what didn't work. Like if anything broke for you, that wasn't the thing that broke for everyone. Let us know. If you saw anything weird, like you couldn't hear someone and you're in the same lobby, or if you couldn't hear me or anything like that, or the audio, or if anything I did, like taking out my headphones, fixed it, please let me know. Really appreciate that. But yeah, that is that. Ask any questions you have. We're happy to debug, and we will be launching open hacking online, which will be taking place through these lobbies, which are going to work by the end of tonight. And that'll be basically just like open space for people to ask questions and get live help and that kind of thing. This is going to be awesome once it works. So yeah, let us know what you think, please. Yeah, I'll just hang around here. Cool. Softmax. Softmax object has no attribute logs. Softmax. I don't know what your code looks like. But it might be, so what we want to do is f.softmax, and in the f is torch.nn.functional, and for torch.nn.functional, all the the functions in it are lowercase. So it might be like lowercase s. Try that. Otherwise, are you doing a .log softmax anywhere where you're trying to get that attribute from this object? Not sure. I can show my code again if you want. So where we were doing the softmax was here. So this is what I mean, that is a lowercase. It's all lowercase. Otherwise, I mean, I can look up your error for you, but I hope you've already done that. Because that's not going to work, is it? Yeah. Okay. Right. Okay. Yeah, let me know if you fix that. TensorBoard running. If you're using Linux, which you're probably not, it's super easy. You need to, okay, a few basic things I can definitely cover now is like, you need to make sure you're in the right directory. Because if I run TensorBoard, if I run TensorBoard here, firstly, it will not work because it's saying I haven't given a logging directory. So if I do give it a logging directory, which is basically where it expects to find all the data in, then it will spin up. And then if you click on that, it will take you here, and this will say there's no dashboards active for the current data set, and you'll be like, why is this happening? But the issue here is that I started TensorBoard in a different directory to where I'm coding. So what do I have? I have this and this. So this one's in CNN's folder, and this one is in my home folder. So I need to cd change directory into that convnets repo before I do the same thing. And then if I run that, it'll work. But yeah, maybe you're having a more complicated issue than that. It's pretty temperamental, to be honest. Happy to go through it if you want, though. Any more info would help. Yeah, absolutely agree with that. Definitely. Sweet. Yeah, cool. That makes sense. So yeah, it's basically like so f is torch.nn.functional, and what that means is it contains like a load of like the functional versions of things that you might want to run. Whereas torch.nn, it has like all these modules, all these classes. So in Python in general, classes start with a capital letter. So this is a softmax class, which you'd need to initialize with brackets on the end of, which would return you an instantiated class, which is then callable. And so then you'd be able to return, if you put some brackets on the end of this, then and said like, okay, my softmax equals torch.softmax with brackets, then you'll be able to call my softmax. Alternatively, you can just call f.softmax and it saves you a few lines. Similarly, I could have written, instead of this, so here I'm instantiating the relu class. I could have just done f.relu like that, because that's already callable, right? So I don't need to instantiate the class, which returns me a callable object. This is a function, hence it's callable. And so that would have been probably a better way to do it, but it's the same thing, like that. Cool. Yeah, defo agree. Anything else? One more person talking apart from me. Was it not me twice, or was it someone else? It might have been my flatmates on the roof. Did you get TensorBoard running? Cool. Yeah, we still use relu. So we use the stack of matrices, the activation maps to we basically once we've done enough processing with our convolutional layers, we should have the values in the activation maps represent something meaningful, and we should have small enough spatial spatial representations of those features such that we can just like flatten them and not lose too much information, because if the images are small, there's less spatial information in there, so there's less information to be lost if we flatten them. So when we flatten them, we hope that they retain all the information that we need, and then we can pass them through either they're already the size we want, or we can just pass them through a linear layer to squash them into the size which we do want. Okay. Cool, right. Nice, everyone's still here. Yeah, please put more questions if you want. I'll hang around till 8:30 because that's when we're meant to be here. Yeah, the website is up and working again now, so you can come back here and ask questions again. Okay. Yeah, TensorBoard is a bit temperamental to get set up, so we'll definitely figure out some way we can help with that. Maybe release a video or a guide or something. I mean, to be honest, I can't help that much because it's so easy on Linux, but it's often on Mac or Windows. It's much harder to set up. Some nightmare bugs. Who's here? Is any of the usual suspects here? Cool. So you should have all just got a feedback form as well emailed to you. So if you could fill that in, honestly, it really means a lot. It means a lot for this session, more than most. So yeah, try and do that, please. Really appreciate it. It's really useful. If there's anything like that went wrong in terms of obviously the software running now, please let us know, because otherwise we might not catch it and it might just be as bad next time, either for you or for everyone else. But yeah, we can definitely try and fix any problems we know of. So let us know what went wrong. Let us know any like features you'd like, or any other kind of suggestions, feedback. We have a lot in the pipeline of stuff ready to come out, based on all the feedback and user interviews you guys did with us. That was awesome. But yeah, if there's anything we think is a really great idea, we'll definitely try and implement it. Move fast. Cool. Yeah, I'll still take questions if anyone's asking any. Go ahead. Can we talk with you here? Yeah, absolutely. So I would love to have the lobby, the group features working, but I don't think it is right now. We'll definitely fix that ASAP. It was working. Obviously, just production is a different game. So I'll have that working by the end of tonight, and then we'll launch open hacking, which will just be like another tile on the web app where you can click and just see who's there hacking away. We can do that. So yeah, but at the moment, sorry, it doesn't look like it's working, so we can't do it right now. But yeah, that'll definitely be fixed soon. And yeah, I'm gonna get straight off this and fix that. I'm gonna get straight off this and fix all the shit that went down today. I built so much in the last like 12 hours. Just trying to get all the features here, this forum, Twitch integration, switching lobbies. I even built it so that teaching assistants could move between lobbies, screen share. God, you have no idea how hard that was to set up. Direct peer-to-peer connection between browsers. But it's gonna be worth it when it works. Cool. All right, I'm going to sign off now. And we'll be back. We'll be back on Thursday with the what is it on Thursday? The Deep RL course, and we'll probably be ramping up the number of workshops we're throwing as well, just because there's not much to do, and we want to get more tests on this software, and we want to like make all of you hack on some useful shit. So yeah, we'll be back soon. Just keep updated with your emails. Please fill in the feedback. Really helpful, and it'll be better next time. But yeah, for now, I'm gonna call it a day.